Let's continue chapter 11. So this is the second video for chapter 11. We are beginning with slide 28 of Phys 8 slides 11.pdf. We learned earlier that momentum can be transferred from one object to another but cannot be created or destroyed. As a result, a system on which no external forces are exerted, which we call an isolated system, has a constant momentum. So momentum is P equals mv, mass times velocity equals momentum. So the momentum is constant. The change in P, change in momentum, is zero for an isolated system, a system on which no external forces act. Today we will learn that angular momentum can be transferred from one object to another, but angular momentum cannot be created or destroyed. So the conservation of angular momentum is as fundamental a result as the conservation of linear momentum or the conservation of energy. So a system on which no external torques are exerted has a constant angular momentum. And angular momentum is the product of rotational inertia times rotational velocity. Last video I called this angular velocity. It can be called either angular velocity or rotational velocity. Those are two names for the same thing. You notice we say angular momentum, we don't say rotational momentum. For some reason, we always say angular momentum. Sometimes one says rotational velocity, sometimes one says angular velocity. We used in this sentence a word that we won't formally see until chapter 12. We used the word torque. So we will learn in chapter 12 that a non-zero torque results from applying a force whose line of action passes some perpendicular distance, and we call that perpendicular distance the lever arm, from the axis of rotation, or from a hypothetical axis of rotation, thus tending to cause rotation about that axis. So torque is to angular momentum as force is to momentum. Non-zero torque tends to change angular momentum. Non-zero force tends to change momentum. Momentum is mass times velocity. It's a measure of how much mass is moving how fast. Angular momentum is rotational inertia times rotational velocity. So it is a measure of how much rotational inertia is rotating how fast. Probably the quickest way to give you some intuition for what this completely new idea, angular momentum, is about is to show you an example that I think will look quite familiar to you if you've ever watched figure skating competitions. If I spin around while sitting on a turntable, and when I'm sitting on this turntable, I am rotationally isolated, and you can look and you can kind of imagine what are the mechanisms that would cause me to change my angular momentum. And the two mechanisms that you'll see in the clip are the friction in the wheel bearings for the turntable, which we've contrived to make pretty small, but it's not zero, but we can assume that it's pretty small, and the push that I give myself when I reach out and touch the lab bench to get myself going. Another possible external torque that would make me not rotationally isolated would be if my feet touched the floor. So you'll notice that I keep my feet where they cannot contact the floor. But if I did contact the floor with my feet, then I would no longer be rotationally isolated. So to think about what rotationally isolated means, I think it helps to imagine what would change my angular momentum. A push against the table would change my angular momentum. My feet touching the floor would change my angular momentum. And significant friction in the wheel bearings of the turntable would change my angular momentum. But once I get going on this turntable, you can assume that for that short time that you watch me, I am, for all intents and purposes, rotationally isolated. So therefore my angular momentum, this product of rotational inertia and rotational velocity, should be a constant. So then what happens when I'm turning around at some rotational velocity omega and I suddenly pull in my arms? And maybe especially if I'm not just pulling in my arms, I'm pulling in my arms while each hand holds a dumbbell. So I have a dumbbell in each hand, and my arms are initially outstretched. So there's quite a bit of mass at a significant distance from my axis of rotation, and then I pull that mass in very close. And so then ask yourself what that does to my rotational inertia, because the rotational inertia is summing up. The rotational inertia is summing up all the little bits of mass weighted by the square of their distance from the rotation axis that together constitute the rigid body that is me when I am rotating on the turntable. So if I take that mass and I suddenly pull it into a much smaller radius, then I'm suddenly decreasing my rotational inertia. And if I'm rotationally isolated, then my angular momentum should be constant. So if the product of these two numbers is constant and I suddenly make the first number much smaller, then I guess the second number has to become much bigger to keep the product constant. Notice where my feet are in this image, so they're not touching the floor. And then notice how far my hands and the dumbbells in my hands are from the axis of rotation in the two cases. This demonstration, by the way, is known as 3 dumbbells on a stool. Can you find the 3 dumbbells? I think we should see omega increase. Let's see if that works. And I think you've seen this work with figure skaters. Okay, so I imparted some angular momentum to myself by pushing off the table, and now I will reduce my rotational inertia by pulling the dumbbells in close to my chest, and you can see that I started rotating at a much higher rate. And whoa! 2 of the hardest parts of this chapter are that there's so much new vocabulary to learn, and that so much of that new vocabulary comes with Greek letters. Fortunately, you can use as a mnemonic device, a kind of memory trick, the very close analog between our linear coordinates from the early chapters of the book and the rotational variables from chapter 11. So we can just reason by analogy. We have been measuring where something is with a position, r, the vector r, which now, since chapter 10, is the ordered pair xy that lies in a plane. So we have an x coordinate and a y coordinate. In chapter 11, we've introduced a rotational coordinate. We've introduced a rotational coordinate theta, which is how far in angle, in fact with angle measured in radians, we've gone from some starting point to some ending point. And in fact, if the circle in which we move has radius r, then the arc length is s equals r theta. So somehow it's a tradition in math to use lowercase s to represent arc length, which is the distance traveled along a path which is not necessarily straight. To describe how quickly something is moving, we have, since the early chapters, been using velocity, which is a vector. And now, since chapter 10, it has 2 coordinates, v sub x and v sub y, the velocity component in the x direction and the velocity component in the y direction. This velocity vector is the rate of change of the position vector, which means that the x component of velocity is the rate of change of the x coordinate, and the y component of velocity is the rate of change of the y coordinate. Our analog in chapter 10 is rotational velocity, which we also sometimes call angular velocity. Angular velocity and rotational velocity are 2 names for the same thing. We use lowercase omega. Greek letter lowercase omega looks a little bit like a lowercase w. Omega is the rate of change of theta. Theta is measured in radians, so omega is measured in radians per second. Omega is d theta by dt. Beware though that because a radian is a dimensionless unit, since it basically is measuring the ratio of this circular arc to the radius, and this is a circular arc measured in meters, and this is a radius measured in meters, so the ratio cancels. So since a radian is formally a dimensionless unit, radians per second is the same as per second. So when doing unit analysis, you drop radians because a radian has no dimension. Although it is usually convenient to write radians so that you remember that you're working in radian. But remember, when you're canceling out units, a radian per second is the same as per second. Since chapter 3, we've been talking about acceleration, and since chapter 10, we've been talking about acceleration in a plane in 2 dimensions. Acceleration is a vector. It is the rate of change of velocity. velocity is a vector, and of course velocity is the rate of change of position, and position is a vector. The acceleration vector has two components. The x component of acceleration is the rate of change of the x component of velocity. The y component of acceleration is the rate of change of the y component of velocity. So we can write that in vector notation as acceleration equals the rate of change of the velocity vector. Now in chapter 11 we have rotational acceleration. This is brand new right now. You're seeing it for the first time. We use the Greek letter alpha, lowercase alpha, for rotational acceleration. Alpha is the rate of change of omega. So rotational acceleration is the rate of change of rotational velocity. Rotational velocity is the rate of change of this rotational coordinate theta. Omega is the rate of change of theta, just as v is the rate of change of x or r. Rotational acceleration alpha is the rate of change of rotational velocity omega, just as acceleration is the rate of change of velocity. So rotational acceleration is to rotational velocity as acceleration is to velocity. And rotational velocity is to this angle theta, the rotational coordinate, as velocity is to position. We learned these results in chapter 3, and they were just, we saw that they were simply math. There was really, the only physics in them was a statement that, let's assume, the only physics was the statement that for some reason we know that the acceleration is constant. And so if you know that, for example, the acceleration in the x direction is constant, then math tells you, okay, final velocity equals initial velocity plus acceleration times time. Final coordinate is initial coordinate plus initial velocity times time plus 1/2 times acceleration times time squared. And then if you put these two equations together and eliminate the time, you can get that Vx final squared is Vx initial squared plus 2a sub x delta x. And this is actually the same result that you often now know how to get using conservation of energy in many cases. So this lets you relate a final velocity to an initial velocity if you know the acceleration and how far you traveled and you don't care about the time. We have a completely analogous set of results now for rotational motion. So if the angular acceleration, the rotational acceleration, sometimes I will say angular and rotational interchangeably. If the rotational acceleration is constant, if alpha is constant, then omega final is omega initial plus alpha t. The final rotational velocity equals the initial rotational velocity plus the rotational acceleration times the time. This is exactly analogous to this. So it's like final velocity is initial velocity plus acceleration times time. Final rotational velocity is initial rotational velocity plus angular rotational acceleration times time. This is exactly equivalent to this, exactly analogous. This is exactly analogous to this. So the final theta, the final rotational coordinate, the final angular coordinate you might say, equals the initial theta. The final theta is the initial theta plus omega initial times time plus 1/2 times alpha times t squared. So this is the final angular coordinate, the final theta. This is the initial angular coordinate, the initial theta. This is the initial angular velocity, and this is the constant angular acceleration. So again, this result is exactly analogous to this result. They're both simply the result of math. This was assuming that the acceleration in the x direction is constant. This is assuming that the angular acceleration is constant. Once you make that assumption, the math tells you these results. And then similarly, this lets you relate the final angular velocity to the initial angular velocity if you know the constant angular acceleration and if you know the change in angle, but you don't care about the time. And one thing to be aware of here is that in these cases, the angle goes around and around and around. It doesn't wrap around, so these angles can be bigger than 2 pi. This is basically how far you've gone in angle, and it may be that you've gone around many times, more than 2 pi radians. Let's get some practice by putting these new results to work so that they seem a little bit more concrete, less abstract, and maybe that will help them to stick. Here's our first practice example working with these new rotational analogs of our previously familiar linear variables. A car accelerates from rest starting at t equals 0 such that its tires undergo constant rotational acceleration. Alpha is 5.9 radians per second squared, which by the way we write as 5.9 per second squared. See, radians per second squared is the same as per second squared. It's the same as second to the -2 power. That takes some getting used to. The radius of each tire is 0.29 meters. At t equals 11 seconds after the acceleration begins, find the instantaneous rotational speed omega of the tire, so I'll call that omega final. Find the total rotational displacement, delta theta, of each tire. Find the linear speed v of the car. I'll call that v final. Assuming the tires stay perfectly round, we're also assuming that the tires roll without slipping. And find the total distance the car travels in the 11 seconds. Well, the car's tires do roll without slipping, so since the wheel is rolling without slipping, every time the wheel goes a distance delta theta in radians, the center of the wheel will go forward a distance r delta theta in meters. So if the wheel goes around 2 pi radians, one full rotation, the car will go forward one circumference of the tire, which is 2 pi r. So omega final is omega initial plus alpha t. So that's this equation. Omega initial is 0 because we started from rest, where the initial rotational velocity is 0, and then we underwent a constant angular acceleration alpha. So this is just 0 plus alpha t. Alpha is 5.9 per second squared, which is the same as 5.9 radians per second squared. And t is 11 seconds. You multiply those two together, you get 64.9 per second, which is the same as 64.9 radians per second. Theta final is theta initial, which is 0. We can just define, we could make a little spot on the wheel here and call that theta equals 0. So we're just going to take our starting point to define theta equals 0. Omega initial is 0 because at t equals 0, the wheel is not rotating. We start out from rest and then we undergo constant angular acceleration of the tires. But then this term is 0, this term is 0. This 1/2 alpha t squared term, which is just like our old familiar 1/2 at squared term, this is non-zero. We plug in alpha is 5.9 per second squared. T is 11 seconds. Remember to square it. You get 357, which is a number with no units. What does that mean? Well, it's 357 radians. And just as a reality check on that, that's about 57 revolutions. So the wheel goes around and around about 57 times in these 11 seconds. Then the distance the car goes forward is the radius of the tire times this delta theta. Delta theta is theta final minus theta initial. So that's 357 times the radius, 357 times 0.29 meters. So this is just like arc length equals r theta. And arc length along their circumference is the same as the distance that the car goes forward because the wheel rolls without slipping. You see how convenient rolling without slipping is. In fact, your car's odometer assumes that your car tires are rolling without slipping, whereas the GPS on your phone doesn't make that assumption. So 357 radians times a radius of 0.29 meters is 103.5 meters. So we've gone a little over 100 meters, about a football field. And then the final velocity in the x direction, in the forward direction, is omega final times the tire radius. So that's 64.9 per second. So omega, radians per second, is the same as per second. 64.9 per second times the radius, which is 0.29 meters, we get 18.8 meters per second. So about 19 meters per second is the car's final velocity. Is the car's velocity at t equals 11 seconds. I guess it's continuing to accelerate. Next, let's look at the loop-de-loop demo. Let r be the radius of the circle in the loop-de-loop demonstration. I want the ball to make it all the way around the loop without falling off. What is the lowest height h at which I can start the ball from rest? So we want the ball to start from here, some height h above the bottom, and it's going to make it all the way around without falling off. And it seems like, if we started it from somewhere down here, it might just get up this far and then slosh back and forth and never make it to the top. But then, maybe we start it from, you say, well, if you start it from 2r above the ground, then it should make it to the top, but maybe then it'll just fall down. So I'll start right around here. So we'll start right around here, and let's let it go and we'll watch what happens. So how high do we have to start it from so that it goes all the way around, doesn't fall off? A, the ball will make it all the way around if the height is at least as big as r. Well, r would only be the middle of the loop-de-loop, so I'm not sure I believe that. The ball will make it all the way around if h is bigger than 2r. Well, okay, then we seem to have enough potential energy initially to reach this potential energy, but then by the time it gets to the top, we've used up all of that potential energy just getting to the top, and we have no kinetic energy, so I guess we would just fall down. If h equals 2r, the ball will just make it to the top and will then fall down, assuming for the moment that it slides frictionlessly along the track. That's another complication. It might turn out that it rolls without slipping. Let's just assume for the moment that it slides frictionlessly along the track. When the ball is at the top of the circle, its velocity must still be large enough to require a downward normal force exerted by the track on the ball. You see, we have to have circular motion. What keeps it going in the circle? What keeps it going in the circle is the normal force exerted by the track on the ball. The push by the track on the ball is exactly analogous to the pull by the string on this ball. The string can only pull, it can't push. Track can only push, it can't pull. It might be different if the track were a little tube, but the track is not a little tube, it's just a track. When the ball is at the top of the circle, its velocity must still be large enough to require a downward normal force exerted by the track on the ball. So the minimum height is even larger than 2r. Just how much higher, I'm still trying to figure out. Well, I think I like C. So the ball starts up here with some initial gravitational potential energy. It starts from rest somewhere up here. And as it goes down the ramp, it goes faster and faster, it speeds up. I guess it seems like it has its maximum kinetic energy down here because all of this gravitational potential energy has been turned into kinetic energy by the time we get down here. And then it makes its way up. And as it goes up around the circle, it must lose speed because it must lose kinetic energy because it's gaining gravitational potential energy. So at the instant when the ball is at the position shown, so here's the center of the hoop, here's the center. So when we're over here at the 3 o'clock position, what direction does the ball's velocity vector point? Well, I think it points up, because for circular motion, the velocity is always tangent to the circle. So at the instant shown in this picture, when the ball is at 3 o'clock, we know the ball is moving upward, and we know the ball is slowing down. Why is it slowing down? It's because Earth's gravity is exerting a downward force on it. So that is slowing it down because its velocity points upward. And there is a downward component of acceleration, which is due to Earth's gravity, so that's slowing it down. So there seems to be an acceleration downward in the y direction, but of course we also know that it's moving in a circle. And if it's moving in a circle, then there must be an acceleration toward the center of the circle. So it seems like this is a pretty complicated situation. We have a vertical downward acceleration due to Earth's gravity, and that is slowing the ball down because the part of the acceleration which is parallel to or opposite parallel to the velocity, parallel to the velocity would speed it up, and then anti-parallel to the velocity, opposite parallel to the velocity, would slow it down, and then a component of acceleration perpendicular to the velocity would not change the speed, but it would change the direction. So we know we have this centripetal acceleration toward the middle, whose magnitude here must be v squared over r. But it seems like at this instant we also have a downward acceleration which is slowing the ball down, which is Earth's gravity. So I think we have only one vertical force here. Maybe it'd be good to draw a free body diagram, but we'll have only one vertical force here, it's gravity. So a sub y is minus g at this instant, but then the horizontal acceleration must be v squared over r, and that must be due to the contact force by the track pushing to the left on the ball. So at this same instant, we know there must be a horizontal component of acceleration. We could call that a sub x, and its magnitude is v squared over r, points toward the center of the circle. And the horizontal force responsible for that is the normal force, the contact force by the track on the ball. So what's happening at this instant is actually pretty tricky to analyze. So the velocity points upward and it's moving in a circle. To keep it going in a circle, there must be a centripetal acceleration that points toward the center of the circle. That centripetal acceleration changes the direction of the velocity vector, but it doesn't change the magnitude of the velocity vector. It doesn't change the speed. So that component of acceleration, points to the left. It points toward the center of the circle, and it's caused by the normal force exerted by the track on the ball at this instant. Then there's a tangential acceleration. So when you're moving in a circle, if your speed is changing, that has to be due to a component of acceleration that is tangential rather than radial, tangential rather than centripetal. So at this instant, the tangential acceleration is due to the force of gravity. So we actually know at this instant that the tangential acceleration is g downward, and we know at this instant that the centripetal acceleration is the normal force divided by the ball's mass, and that must equal v squared over r. So we have those two components of acceleration. So the acceleration at this instant must actually point sort of southwest, because you know there's a downward part because the ball is slowing down, and you know there's a leftward part because you know the ball is moving in a circle. But this instant is kind of complicated to analyze. I mention this instant because at this instant you can clearly separate the one part due to gravity, which is tangential, and another part due to the normal force, which is centripetal. But we're really interested in this instant at the top, where of course gravity still points down, but the normal force, if there is one, will also point down. Now let's suppose the ball makes it all the way around the circle without falling off. That's what we want to happen. At the instant when the ball is at the position shown, the top of the circle, what do we know about the vertical component of the ball's acceleration vector? Well, if it continues going in a circle successfully, then this vertical acceleration must be v squared over r downward. So if this vertical acceleration is not equal to 0, then what vertical forces are responsible? Well, I think there are two forces responsible. Gravity points downward, and the normal force exerted by the track on the ball points downward. Now, remember, the track can push on the ball, the track cannot pull on the ball. And that's analogous to this idea that the string can pull on the ball, the string can't push on the ball. It's also analogous to this idea that the bucket could push on the water. The bucket could not pull on the water when I was spinning the bucket of water around. So I think we need to make sure that the ball, when it reaches the top, is going fast enough that the normal force required to keep the ball moving in a circle is pointing down rather than up, because you know the track is capable of pushing down on the ball when the ball's at the top. The track is not capable of pulling up on the ball when it's at the top. It might be if it were like a tube, but it's not a tube, it's just a flat track. Let's suppose the ball makes it all the way around the loop-to-loop with much more than sufficient speed to stay on the circular track. Let the y-axis point upward, and I guess we're letting the x-axis point to the right. Let v top be the ball's speed when it reaches the top of the loop. What is the y component, a sub y, of the ball's acceleration when it is at the very top of the loop? I think it's minus v top squared over r when it's at the very top of the loop, because in order to keep moving in this circle of radius r, there must be a force toward the center of the circle, which is centripetal, toward the center of the circle, whose magnitude is v squared over r. And because we defined the y-axis to point up, then this must point down, so that's a sub y is minus v top squared over r. So I think I like answer D here, delta. It's easy to fool yourself into thinking there's an additional little g in there, but really you know that it's going in a circle of radius r, and it's moving at speed v, or v top. So to continue moving in that circle, its acceleration toward the center of the circle, which is its acceleration in the minus y direction, must equal v squared over r, v top squared over r, since it's at the top. Well, we're calling it v top. The track can push on the ball, but the track can't pull on the ball. How do I express the fact that the track is still pushing on the ball even at the very top of the loop? I could write the equation of motion for the ball, F equals ma on the ball, and require the normal force exerted by the track on the ball to point inward, even at the very top. At the very top, inward means downward. If the equation F equals ma on the ball gave us an outward pointing normal force exerted by the track on the ball, that would be inconsistent with the ball staying in contact with the track. I think that's right. That actually sounds pretty good to me. because then in order to stay on a circle, see, imagine that you get to the top. Imagine that you get to the top and the ball is not moving. The ball just reaches the top but it has 0 speed. What's the track going to do? The track, actually the way I drew it here, it's kind of bad the way I drew it here. The track can't do that. The track can only push on the ball. The track can't pull on the ball. See, so it would be as if you get to the top and maybe the track needs like some kind of magnetism to hold the ball there. It can't do that. It can only push against the ball. So if the ball reaches this point and it stops, then it will just fall down. Oh, B, use conservation of angular momentum. Why not? It's a brand new chapter 11 topic. Well, I think conservation of angular momentum is not really relevant here. And one reason it's not relevant is we have an external torque due to gravity for a good chunk of the motion. Oh, draw a free body diagram for the ball and require the gravity and the normal force point in opposite directions. I don't think they want to point in opposite directions, actually. I think they want to point in the same direction. Draw a free body diagram for the ball and require that the magnitude of the normal force be at least as large as the force of gravity on the ball. No, I think we want to require that the magnitude of the normal force be at least, well, we want the normal force to point downward. It could be just barely non-zero. It could even be exactly 0. But we need to make sure the normal force does not point up there, because if the normal force pointed up there, that would require the track to pull on the ball, but it only knows how to push on the ball. So I guess the only one that I like here is A. By the way, I wrote down, but I neglected to mention, at this instant when the ball is at the top, the tangential acceleration is 0 because there are no tangential forces, unless you think that it's possible, I guess, that friction is slowing the motion down a little bit. But neglecting friction, there are no tangential forces. So gravity is centripetal here, and the normal force is centripetal here. So the tangential acceleration at this instant, unless you're going to somehow count friction or air resistance, is 0. So as you scrutinize this slide, let's write down F equals ma for the y component. So it seems like we can use this free body diagram to write the y component of F equals ma, and let's let the normal force point downward, and we want to get a normal force which is bigger than 0 for the ball to stay in contact with the track. If it's less than 0, then the ball falls off the track. So I think we find ma sub y, and by the way, a sub y is minus v top squared over r. That would be minus mg, because that's downward, minus f normal. So we have minus mv top squared over r is minus mg minus f normal. Minus mv top squared over r is minus mg minus f normal, with f normal bigger than 0. I think I like h here, hotel. Minus mv top squared over r equals minus mg minus f normal. And you want f normal to be bigger than 0. So writing down f equals ma, and then solving for the statement that f normal is bigger than 0, tells you need v top squared over r to be bigger than g. And that means that you want v top to be bigger than the square root of gr. So now what does that imply for how much initial gravitational potential energy you need so that you have at least that big a speed when you get to the top? So let's consider the balance of energy between the initial state when the ball is at rest at its starting position at height h above the ground level, at height h above the bottom of the loop-de-loop, versus the state which seems to be the critical point when we are at the top of the loop-de-loop, because the whole point is that we want to have enough speed at the top of the loop-de-loop that we make it around. That means our speed at the top of the loop-de-loop has to be bigger than the square root of gr, where r is the radius of the loop. So our initial energy when we're at rest at the top is mgh. That's all gravitational potential energy. And then at this critical point where we care about having at least a speed whose magnitude is at least gr, well, where are we? We're 2r above the bottom of the loop, so that's mg2r. And then we have some kinetic energy, so that's 1/2 m v top squared. It has to be at least v top squared, so the minimum possible kinetic energy is 1/2 m v top squared, with v top equals the square root of gr, so v top squared equals gr. So v squared is gr. It seems like the minimum height from which we can release the ball and have it make it all the way around the loop-de-loop is 2.5 r. Now this is assuming that the ball just has translational motion, that all of the ball's initial gravitational potential energy goes into translational kinetic energy of the ball. But what if there's also a rotational part of the ball's kinetic energy? In other words, what if the ball is actually a solid sphere that rolls without slipping on the track? Oh no. Then this 1/2 mv top squared has to have an additional component. That's kind of a tricky add-on that we could probably ignore, but let's see how big it would be if we didn't ignore it. So if you do the math, then you have initially mgh, gravitational potential energy, and you're still going to need that gravitational potential energy at the top where your height is 2r above the bottom of the loop. And then you're still going to need 1/2 mv top squared translational kinetic energy in order to undergo circular motion with the minimum necessary speed v top, where v top has to be at least the square root of gr, so v top squared has to be at least gr. But then you have this rotational kinetic energy term, 1/2 I omega top squared. If the ball is rolling without slipping, then omega top equals v top divided by this little r, we'll call that the radius of the ball. We actually aren't going to care what the radius of the ball is, it will cancel out, but we have this new variable, the radius of the ball itself. Now for a solid sphere, the rotational inertia is 2/5 times the mass of the ball times the radius of the ball squared. 2/5 m r ball squared for a solid sphere. So then this additional term that we need is 1/2 I omega squared. This is 1/2, and the I is 2/5 m r ball squared. And then the omega is v top over r ball, and we're going to square that. So then you see the r ball cancels out, and you get 1/5 the mass of the ball v top squared. So that just gets added to this 1/2 the mass of the ball v top squared. So instead of a half, you have a half plus a fifth. A half plus a fifth is 7/10. So mgh, that's the initial gravitational potential energy. Here's the final gravitational potential energy, final being at the top. And then here's the translational kinetic energy, which we've re-expressed to be 1/2 mgr using this. And then here's the 1/5 mgr. So the height has to be at least 2.7 radii above the bottom, it turns out, if you say that the ball rolls without slipping and is a solid sphere. So the reasoning required to get answer C, Charlie here, mgh equals 1/2 m v top squared plus 2 mgr, with v top equals square root of gr. So I hope that you can, with a little bit of effort, follow that. This is using the conversion of potential energy into kinetic energy, and then it used our free body diagram for the motion at the very top of the circle, the very top of the loop, to figure out the minimum speed, which we figured out by imposing the constraint that the normal force had to be downward rather than upward. The additional step to go from 2.5 r to 2.7 r is pretty tricky, so that might be like extra credit level tricky. So this slide, slide 41, sums up the argument that we just made at the bottom here, which got us from 2.5 r to 2.7 r. So we start out with mg8, and we turned it into 1/2 mv top squared plus 1/2 I omega top squared plus 2 mgr. This is 2 mgr because we have to make it to 2r above the bottom, and 1/2 mv top squared, and we worked out with the free body diagram that v top has to be at least as big as the square root of gr, and then if the ball rolls without slipping, then omega top is v top over the radius of the ball itself. So r ball is the radius of the ball itself, big R is the radius of the loop-to-loop. So we do this, we get this 2.7 r. So I guess I'd like it if you can follow your way to answer A. Following your way additionally to answer B, I'd say, is kind of an extra credit level understanding. And there's that final result summarized on slide 42. Let's try some intermediate height. Let's see if we can tell by ear where it seems just barely to lose contact with the track. Oh, let's try a little higher than that. Huh. Well, it made it around, but it clearly lost contact with the track. What if we start from somewhere around here? What if we start from a little higher than that? What if we start from a little lower than that? Ah, can you hear that it was silent for an instant? It lost contact with the track and you didn't hear the friction noise? So you can hear, I think, for a moment, it loses contact with the track. And I think if we started a little higher than that, then I think it stays in pretty good contact with the track. And let's start it even a little higher than that. You accidentally knock a full bucket of water off the side of the well shown in the figure. The bucket plunges 18 meters to the bottom of the well. Attached to the bucket is a light rope that is wrapped around the crank cylinder. How fast is the handle turning? What is its rotational speed when the bucket hits the bottom? The inertia of the bucket. The mass of the bucket and water together is 13 kilograms. The crank cylinder is a solid cylinder of radius 0.65 meters and mass 5 kilograms. Assume small handle's mass is negligible compared with the crank cylinder. It's a solid cylinder, which is like the axle of our well. And this is a bucket, and the bucket is filled with water. Somehow we know the mass of the bucket and water together. And initially it's resting on the edge of a well, and there's a rope tied to the bucket. And then the rope is wound around the axle many, many times. And initially nothing is moving, and the bucket is up at the top of the well. Suddenly the bucket falls, and as the bucket moves down in a straight line, this axle goes round and round like this. Okay. How would you approach this problem? Initial angular momentum of bucket equals final angular momentum of cylinder plus bucket. Well, we haven't learned enough to be able to do that yet, and I don't think it would work because it turns out that Earth's gravity pulling on the bucket is causing the cylinder to rotate at a faster and faster and faster angular velocity. That's an external torque. So angular momentum is not constant. Initial gravitational potential energy equals final kinetic energy, where we include the translational kinetic energy for the bucket and the rotational kinetic energy for the cylinder. I think I like that. Initial gravitational potential energy equals the final kinetic energy of the bucket. Well, C would be ignoring the kinetic energy, the rotational kinetic energy of the cylinder. So I don't like C. How about just the final KE of the cylinder? See, again, I don't like D for a similar reason. We have to include both parts of the KE. Initial KE of bucket equals final GPE. That doesn't make much sense. Initially, no, that's like 0 equals 0, right? Use torque equals mgr to find constant angular acceleration. You know, that in principle might work, but we don't know how to do it yet. We won't know how to do it till the next chapter. I think we're going to use conservation of energy, and we're going to make sure we account for both kinds of kinetic energy, the rotational kind and the translational kind. Let's do it. So I won't work this all the way through to a solution, but I think these are all the pieces. So you have the initial energy is just gravitational potential energy. It's the mass of the bucket, including its water, times g times the height of the bucket. And then at the end, the bucket has fallen down to the bottom, so all of that gravitational potential energy has been converted into other forms. And if we're assuming there's no friction that matters, then it's all kinetic energy. So we have translational kinetic energy of the bucket. That's 1/2 mass of the bucket, V final squared of the bucket. And we have 1/2 rotational inertia, final rotational velocity of the cylinder. And then, now this is interesting, this is similar to rolling without slipping. Every time the cylinder goes around 2 pi radians, the rope goes down with the bucket by 2 pi r in height. So it's because, this happens because the rope is tightly wound around the cylinder. So it can't be loosely, it has to be wound tightly enough around the cylinder and the rope doesn't stretch, so that pulling the rope down by 1 circumference worth makes the cylinder turn around by exactly 1 revolution. So if you can guarantee that that's true, then you have this nice relationship between the velocity up and down of the bucket and the rotational velocity around and around of the cylinder. And then we're told that the cylinder is a solid cylinder, so we can just look up in our favorite table of rotational inertias that the rotational inertia of a solid cylinder of radius r, mass m, is 1/2 mr squared. And remember, this is the mass of the cylinder, which is different from the mass of the bucket with its water. So I think that's all you need to solve the problem, because you can just plug this in and then everything is in terms of omega final. and you have all the masses. What is the rotational inertia for a solid cylinder? Well, I would say it's 1/2 mr squared. How do you relate v of the bucket with omega of the cylinder? Well, we can do this, and why is it true? It's true because the rope is wrapped around the cylinder in a way that pulling the rope down by one circumference of the bucket by one circumference of the cylinder causes the cylinder to turn around one full rotation. Why is angular momentum not the same for the initial and final states? Well, we haven't studied torque yet, but it turns out that the external force of gravity acting on the bucket is applied in such a way that it tends to make the cylinder rotate faster and faster. So that's an example of being rotationally non-isolated. That's an external torque, even though we won't know until next week what torque means. Oh, what are the two expressions for angular momentum used in chapter 11? We'll get to that in a minute. Does anyone know why using torque as mgr wouldn't give the right angular acceleration? Well, actually, I think you would get the right acceleration if you use torque as tension times the radius, where t is the tension in the rope. You see, mg isn't correct because the bucket is accelerating downward. But I don't want to get into this yet because it's chapter 12 and we're not in chapter 12 yet. There actually are two expressions for angular momentum in chapter 11. I think we're not going to get to them until a little bit later. One of them is just I times omega. So that is rotational inertia times rotational velocity. The other is basically momentum times lever arm. So this is mass times velocity times perpendicular distance. And the way to see that, although I think it won't be clear until we use it a little bit later, imagine that I have a pinwheel here. And then imagine if I take a baseball and I throw the baseball at the pinwheel. Well, if I throw the baseball in a way that it goes right through the axle of the pinwheel, then it has no tendency to make the pinwheel rotate. But if I do throw the baseball in a way that it hits with some non-zero perpendicular distance. In other words, if I take the distance of closest approach of this velocity vector with the axle, then somehow this mass times this velocity times how far away I am from that axle has a tendency to make this pinwheel rotate. And we're going to use this later. In fact, you sort of saw me use that when you saw the 3 dumbbells on a stool, because the way I got started was to get a little momentum push at some perpendicular distance from the axle by reaching out with my arm and pushing off against the bench top. So you can use linear motion to create a rotational motion if you apply an impulse, a momentum, a mass times velocity, which has some lever arm, some perpendicular distance away from the axis of rotation. Let me just point out that table 11.3 of your textbook contains a table of rotational inertia values for common shapes. And for a given shape, the rotational inertia value will depend on the axis of rotation. So you need to know not only the shape, but also about what axis it is rotating. Since, for example, if I rotate this pen along this axis, the mass is not very far from the axis of rotation. If I rotate it about this axis, then the mass is much farther away from the rotation axis. So the rotational inertia should be bigger this way, smaller this way. It's the same total mass, but here it's close to the axis. Here it's far away from the axis, so that makes a difference. This table is reproduced in the equation sheet. The equation sheet is like 40 pages of information, so calling it a sheet is a little bit of a misnomer. Here's a second page of these tabulated rotational inertia values. A long, thin rod is pivoted from a hinge such that it hangs vertically from one end. The hinge is at the top, so it can pivot like this. The length of the rod is given. You want to hit the lower end of the rod just hard enough to get the rod to swing all the way up and over the pivot. So you want it to swing more than 180 degrees. How fast do you have to make the end go? So I guess you want to swing it. So I guess you want to hit it hard enough that this goes up here, so then it winds up oriented like this. And it's just barely hard enough, so by the time it gets up here, it basically has, so you want some initial velocity down here, and then if it's just barely hard enough, and it just makes it over the top, then you basically have V final equals 0, or V final is just a tiny bit bigger than 0 when it makes it up to this orientation. We have a thin rod suspended from one end about this axle. And I'm going to hit it in such a way that, you know, the bottom end starts moving with some initial speed v. How big does this initial speed v have to be such that it just barely makes it over the top? So here v is going to be too small. Okay, it doesn't come anywhere near making it over the top. And here I'm going to make v too big. Whoa, okay, it went around multiple times, even though we lost some energy to friction in real life. Say, what happens if I try to hit it just hard enough that it just makes it around? Oh, that was perfect, right? Oh, that was just a little bit too small. Good. That was probably a little more than we needed. It seems like the final kinetic energy is 0. And it seems like the final gravitational potential energy is basically the initial gravitational potential energy plus, well, the center of mass goes from this position to this position. So I think, see, this is L, there's a half L, there's a half L. So I think the center of mass goes from here up to here. The center of mass goes up by a distance L vertically. So gravitational potential energy in the final state equals gravitational potential energy initial state plus mgl. So the whole thing just goes up to, the center of mass goes up to L higher. So this final kinetic energy is 0. But then the initial kinetic energy is what to make that happen? Well, I guess we know how big the initial kinetic energy has to be. It just has to be equal to mgl. But how do we write the initial kinetic energy? Because there's going to be a translational part, the center of mass is moving, and there's going to be a rotational part because it's rotating about its own center of mass. We have a list of statements here. I guess we're supposed to find one which is false. I know the change in gravitational potential energy from initial to the desired final state. So the initial kinetic energy, which is rotational of the rod, needs to be at least this large. Well, I think A is a true statement except that is it rotational or is it rotational plus translational? And we could answer it both ways, it turns out. I'll show you that. So if you're considering this to be the axis, which is a sensible choice of axis, then it is indeed entirely rotational. But if you consider the center of mass to be the axis, then there's a rotational part and a translation. And the way you connect those two statements is this result called the parallel axis theorem. I'll tell you about that in a minute. The book, or the equation sheet, gives the rotational inertia for a long, thin rod about its center. Oh, so then I could use the parallel axis theorem to get the rotational inertia for the rod about one end. That actually is true. The angular momentum, L equals I omega, is the same for the initial and final states. Well, I think that's certainly not true because in the initial state, the rod is moving, and in the final state, it's not moving, or it's just barely moving. So I think it must be rotating at different rates, and yet it's the same, it has the same rotational inertia because the spread of the mass from the rotation axis, or from the center of mass, depending on which way we're looking at it, is the same. So I think C has to be wrong. Because the rod pivots about one end, the speed of the other end is V equals omega L, where L is length. Oh, that's very interesting. That's true. So this is omega I times L. Well, that's good to know. No, okay, yeah. So the only statement that's false is C, Charlie. But then we have to be very careful about what we call rotational, what we call translational kinetic energy. So let's think about that. One way to look at this is to say that if this is moving at speed v, then I guess this will be moving at speed v over 2 because they're all going around at the same omega. So I guess this is like v over 2. So this problem seems to have many moving pieces in a manner of speaking. So here's the length L of the rod, and we want to know how fast we have to make the bottom end move. So if the bottom end moves at some speed v, well then because it's actually pivoting around one end, this end is not moving, this end is moving at speed v, so the middle, the center of mass of the rod must be moving at speed vi over 2. And then we can look up in the table that the moment of the rotational inertia of a rod about its center of mass is 1/12 ml squared. So you say, okay, the center of mass is moving at v over 2. And then meanwhile, the whole thing is rotating. And this is kind of interesting. The rotation rate is given by the speed of the end here is omega times the length, because this is the speed, a distance L away from this rotation axis, and this traces out an arc of a circle. So you can use the same arc length equals angular velocity times radius to get this linear speed equals this angular speed times this distance from the rotation axis. So we can write the translational kinetic energy is 1/2 mv squared, where we want actually the speed of the center of mass. So the speed of the center of mass is 1/2 of the speed of the end. So this would be like 1/2 vi over 2, the quantity squared. And then we want 1/2 I omega squared, and we could use this relationship between v and omega. And then we have to look up this value of I. So if you multiply this out, this is 1/8 mv initial squared, where this is the initial speed of the end, not the center of mass. And then this is 1/2 I omega squared. So omega, we said, is just the speed of the end divided by L for this geometry. And then we looked up the rotational inertia. So this is 1/8 mv initial of the end squared, and this is 1/24 mv initial of the end squared. You add those up, this is 3/24 plus 1/24 is 4/24. 4/24 is 1/6 mv initial squared. That all seems pretty tricky, but I guess it would get you an answer. You'd say 1/6 mv initial squared must equal mgl, and then I guess you're done. Let's see if we can analyze it a different way. What if somebody told us that the rotational inertia of a rod about one end is 1/3 ml squared? And let's just say somebody whispers that in our ear, and we'll figure out in a minute how do we calculate that. Well, if we have the rotational inertia of the rod about the end, then we can consider all of its motion to be rotational, not translational, because it's all about that rotation axis. So you see, what you consider translational, what you consider rotational, depends on what point on the object you choose as your reference point. Normally we choose the center of mass of the object as our reference point, and then we talk about rotation about the center of mass and translation of the center of mass. But we could pick this end of the object as our reference point, which makes sense in this case because there's a defined rotation axis for this problem. In that case, the motion of this reference point is 0, so there's no translational component, and we can consider it all to be rotational, but in order for that to work, we have to know the rotational inertia of the rod about this axis. So if somebody whispered it in our ear, and we'll work it out in a minute. So let's see what happens if we do that. If we do that, then the initial kinetic energy is 1/2 I omega initial squared. So that's 1/2. And then somebody told us that this rotational inertia is 1/3 ml squared. And then we know that omega is v over L. And then multiplying that out, we get 1/6 mv initial squared. Well, that's good. We got the same result here as we got here. And it makes sense because the physics should be the same. It's just the way we looked at it. In one case, we said we're going to consider part of the motion to be translational of the center of mass and part of it to be rotation of this rod about its own center of mass. And then we got this kind of complicated result up here, but it got us the same final answer as this. The simpler way to look at it, although it involves somebody telling us the answer for the rotational inertia about one end, is we say, well, we're going to take this end as our reference point, and then the reference point is not moving, it's not translating, so all of this motion then is rotational. So then we can simply write 1/2 I omega squared. We don't need to worry about a translational part, and that got us much more directly to the same answer. So now we want to know, so we like that. So for solving this problem, I guess we can say this expression for the initial kinetic energy equals mgl, because that's the change in gravitational potential energy, and then we're done as long as there's no friction to dissipate energy. But where did this expression come from? So suppose we're given the rotational inertia of an object about its center of mass, but we actually want to make it pivot about some axis which is displaced from its center of mass by a perpendicular distance d. And I mean, by perpendicular, I mean it's distance from the axis. By perpendicular distance, I mean perpendicular to the rotation axis. So the rotation axis is the plane of the board here. So really, it's just this distance. So we have this distance d between the center of mass and the actual axis of rotation. Now, if you work out the kinetic energy about this axis, you'll have two terms. One term is 1/2 I omega squared, and the other term is 1/2 times the mass times the speed of the center of mass squared. And the speed of the center of mass for rotating about this axis is omega times d. So when you think about it, every time this object goes all the way around the new axis, it also goes around itself. Here's a funny shaped object, and I can hold it basically by its center of mass, and I can make it go around once around its center of mass. Now what if I instead instead pivot it around some other axis, like this axis. Well, notice that in order to get around this axis once, it winds up rotating also about its center of mass once. So to work out the value to relate omega to how far the end moves, we notice that every time it goes once around the new axis of rotation, it also actually rotates once about its own center of mass. So following this through, we get that the kinetic energy is 1/2 I omega squared plus 1/2 m, and then this VCM, the speed of the center of mass, is omega d. So that's omega d squared. So this is 1/2 I omega squared. And this is 1/2 md squared omega squared. So rewriting this same expression up here, we have 1/2 I omega squared plus 1/2. So this is m omega squared d squared. Let's move the omega squared over to the right. So this is 1/2 md squared omega squared. So this kinetic energy is 1/2 I plus md squared omega squared. So it's as if I was replaced by I plus md squared. This is called the parallel axis theorem. So this is the way you prove it. You basically just show that the kinetic energy, if you want to write the kinetic energy about this axis as an entirely rotational kinetic energy, then you have to include the translational part. When you include the translational part, you get this extra term, and that's effectively the same thing as replacing the rotational inertia by the rotational inertia plus the mass times the distance from the center of mass squared. In this particular case, the distance from the center of mass is L over 2, because we want to go from the middle to the end, and the end is L over 2 away from the middle. So then we would have I about the end is I about the center of mass plus m L over 2, the quantity squared. So this is 1/12 ml squared, and then this is 1/4 ml squared. You add 1/12, 1/4 is 3/12, so you put that together, you get 4/12, which is 1/3. So that's 1/3 ml squared, which is the same result we wrote up here. So to answer this question, if it's 1/12 ml squared about its center of mass, then about one end it is 1/3 ml squared. So that's answer D. Suppose I have a solid circle or a solid cylinder like this, mass m, radius r. And instead of making it turn about its own axis like this, suppose instead I want to make it turn about maybe I want to make a pinwheel out of it. I don't know. I want to make it somehow revolve instead about some axis which is displaced a distance d from its center of mass. And maybe I'm doing this with many such objects. But anyway, for the moment, let's suppose it's just this one. And I want to know, what is this thing's rotational inertia if I consider it to be rotating about this axis instead of rotating about its center of mass? Notice that every time it goes around that axis, it actually revolves once about its own axis as well. So it would not be correct to say that its rotational inertia about this point is just md squared, because the md squared would be like the rotational inertia of a tiny little point, a concentrated mass, concentrated at a very small distance, much, much smaller than d, going about that circle. But instead, we want to treat both this object rotating about its own center of mass and the fact that the center of mass is going about this axis. So the parallel axis theorem lets us do that. And again, this works by analogy with that kinetic energy calculation that we did for the rod about its end rather than about its center. It's the same idea. If you want to understand the kinetic energy of this object not about its own center but about this displaced center, you could treat the motion of its center of mass separately from the motion of itself about its own center of mass. But a shortcut is to use the parallel axis theorem. And if you use the parallel axis theorem, then you can treat all of the motion as if it were rotational. So then we have I about this displaced axis is I about the cm plus md squared. In this case, the rotational inertia about this object's own center of mass, if it's a solid cylinder or a solid circle, it would be 1/2 mr squared, and then we would add an additional md squared term to account for the fact that its center of mass is displaced a distance d from the axis of rotation. And we say d perpendicular because you want to measure distances perpendicular to the axis of rotation. Okay, so one more time, the rod. We know that the rod about its center of mass would be 1/12 ml squared. And we want to know, well, what instead would be the rotational inertia of the rod about one end. So in this case, the distance d from the end to the middle is L over 2, which is the familiar result we worked out a couple times already now. So which answer do we like? I think we like answer D, delta, 1/3 ml squared. By the way, the 1/12 ml squared result for the rod about its center of mass appears here in table 11.3 of the book, which is also reproduced in our equation sheet. I think you will usually just look these up, but I think these 6 cases basically cover everything you're likely to use often. A cylindrical shell or a hoop where all the mass is out at radius r, that's mr squared when it's about this axis, the way we've seen it. A solid circle or cylinder is 1/2 mr squared. A hollow sphere is 2/3 mr squared. A solid sphere is 2/5 mr squared. A long thin rod, that means that this dimension is much bigger than this thickness. About its center of mass is 1/12 ml squared, where L is the full length. And then if you do the same thing about one end, we saw this, we worked it out, it's 1/3 ml squared. By the way, if you're curious where that 1/12 ml squared comes from, we can take this rod and say, let's integrate, and we'll say this is a chunk dm, and it's going to be the total mass divided by the total length times dx. And we'll let our x-axis point this way. Here's x equals 0. So then the distance from the rotation axis is just the absolute value of x. So r squared is x squared. So then the rotational inertia is the integral of x squared, and dm is m over L dx, and we integrate from minus L over 2 to plus L over 2. And there we are, ml squared over 12. And I also worked it out for you on slide 54. You don't need to know how to do that. You can just use that if you're curious. You have a weekend job selecting speed limit signs to put at road curves. The speed limit is determined by the radius of the curve and the bank angle of the road with respect to the horizontal. Your first assignment today is a turn of radius r at a bank angle of theta. What speed limit sign should you choose for that curve such that a car traveling at the speed limit negotiates the turn successfully even when the road is wet and slick? So what that means is that at this speed, the car stays on the road even when friction becomes negligible because the road is wet and slick. Draw a free body diagram showing all of the forces acting on the car when it is moving at this maximum speed. Your diagram should also indicate the direction of the car's acceleration vector. This is an interesting problem. So let's start working on this by let's start this by drawing a free body diagram for the car, for the case where the car's speed is at exactly the value for which no friction at all is needed to keep the car moving on its circular path. In that case, let's figure out what the forces are acting on the car. So actually, in that case, there is no friction. First, just to make sure the scenario is clear, here is an elevation view. Elevation view means I'm looking at it from some horizontal distance away. And so let's say the up vector, like gravity actually points down this way, so up points that way. And this is exaggerated, but the car is on the road. The center of the circle is here. So the car is navigating a turn. So the car is going like this, and the center of curvature of the off-ramp is way over here, a distance r away. So this is horizontal. And the road is not horizontal. The road is banked at some angle theta with respect to the horizontal. And in this case, the car's velocity vector points into the board. So the car is moving into the board in this elevation view. And because it's moving around a circle at constant speed, it must be accelerating toward the center of the circle. So that's a centripetal acceleration, v squared over r, that points toward the center of the circle. and the center of the circle is directly horizontal from from the place where the car meets the road. Here is a so-called plan view. So the plan view, now we're looking down from above the scene. So the down direction points into the board. And when we look down, we see the curved road and we see the car. You see, notice here we just saw two tires because we're kind of looking from behind. So you see this is both left tires together, this is both right tires together. Here when we look down from above, we see all four tires because the car is moving in this direction. So the velocity vector of the car in this plan view points up. The acceleration vector, when I say up, I mean the velocity vector of the car points this way in the diagram, but of course that's horizontal. The up direction in this plan view is toward me, out of the page of the paper. And then the acceleration vector points horizontally to the center of the circle. Here's this big circle radius r that is the curve in the road, which is banked somehow for some particular speed. So from this point forward, this is the useful diagram because it lets us show gravity and it lets us show the centripetal acceleration. This plan view is useful for seeing what's going on, but it's not useful for working out the physics. So I'll erase this and we'll do the math here. So let's draw a free body diagram for the car, and we'll be inspired by this elevation view. We'll choose the y-axis to point up opposite gravity. We'll choose the x-axis to point to the right, and the center of curvature is to the left. So the car is accelerating to the left. So the car is moving around the circular curve at constant speed, so its acceleration points toward the center of the circle that defines the bend in the road. It's like a circular arc of a road, and the acceleration has magnitude v squared over r. So the acceleration in the y direction must be 0, the acceleration in the x direction must be minus v squared over r. So let's think about the forces acting on the car. Here is gravity by Earth on the car. It's just the weight of the car. Here's the normal force by the road on the car. And this must be an angle theta away from the vertical, because if the bank angle were 0, then the normal force would be vertical. The bank angle is theta, rotated to the left, so the normal force is rotated to the left by an angle theta with respect to the vertical, so that it is perpendicular to the surface of the road. So this green line, in case I didn't point it out before, this green line is the road surface. Seems like we want to decompose this normal force into two components. Let's decompose it into F normal cosine theta and F normal sine theta. I know this is sine theta because if I redrew a copy of it up here, then I would have this F normal, this dotted vector divided by the original F normal is opposite over hypotenuse, which is sine theta. So this over the original vector is sine theta. So this is F normal sine theta. And then this is F normal cosine theta because this divided by the original vector is adjacent over hypotenuse. So that's cosine theta. You might ask, where is friction? Why haven't I drawn friction? But we are considering the case where there is static friction. Static friction is available, but the speed of the car so perfectly matches the bank of the road that 0 static friction is needed to keep the car on the road. And that's ideal for wet weather, because then if the speed of the car is a little bit different from the ideal speed, then what little static friction is available can keep the car on the circular arc of a road. It seems like the math that we get out of this is that a sub y equals 0 equals up minus down, F normal cosine theta minus mg. And then ma sub x equals minus mv squared over r equals, well, there is no right, there's only left. That's minus F normal sine theta. So this first equation seems to give us F normal equals mg divided by cosine theta, which is a kind of funny looking result. And this second line gives us mv squared over r equals F normal sine theta equals mg over cosine theta sine theta equals mg tan theta. So that's a pretty interesting result, and if you need to use it on a problem, you should work it out for yourself instead of just taking my word for it, and you should start by drawing your own diagram. But it seems like the bank angle for a perfectly banked road is such that v squared over r equals g tan theta. A Ferris wheel rotates at constant speed. Draw a free body diagram for each numbered carriage. For scale, draw MA on each free body diagram instead of the usual A. That way it works out with the same scale factor as forces. Then the two force vectors must sum to MA. For a realistic Ferris wheel, MA would be much smaller than MG, but to make drawings that really bring out the physics, let's make MA be half the size of MG. Whoa, this will be a pretty exciting Ferris wheel. In other words, for the sake of illustration, we'll spin the Ferris wheel fast enough that v squared over r equals 1/2 g. Whoa. So first, let's consider the acceleration vector for each one of these carriages. I don't like the original problem's numbering. I'm going to give them clock numbers. I'm going to call this one 12, this one 3, this one 6, and this one 8. The carriages are going around in a circle at constant speed. This is uniform circular motion. The acceleration of each carriage points toward the center of the circle. So which direction is carriage number 12 accelerating? Toward the center of the circle. Which direction is carriage number 3 accelerating? Toward the center of the circle. Which direction is carriage number 6 accelerating? Toward the center of the circle. Which direction is carriage 8 accelerating? Toward the center of the circle. And then we want m times a to equal 1/2 mg, just so we can make the arrows look nice. This is a very intense Ferris wheel. It's going to have v squared over r equals g over 2. This is like a super intense Ferris wheel. So let's look at 12. Here's a free body diagram for number 12. So I think in order to make this work, I have to make the contact force between the frame and the carriage point that way. So the contact force exerted on the carriage by the Ferris wheel structure points upward, and the gravitational force by Earth on the carriage points downward, and the acceleration of the carriage points downward, and we said it had magnitude 1/2 g. So this line should be half the length of this line, and then we want this line and this line to add together to make this line, so this line has to be half the length of this line and point upward. So that was interesting. So this is the free body diagram, I think, for carriage number 12, with this kind of unrealistic situation that v squared over r is g over 2. And by the way, this contact force by the Ferris wheel structure on that carriage, you could equivalently say that this is the contact force exerted by the Ferris wheel chair on the person riding in the seat. So you want to say, what force does the Ferris wheel seat need to exert on the person to keep the person going around? It's going to be the same answer, just scaled by the masses, as the contact force that the Ferris wheel structure has to exert on the carriage to keep it going in that same circle. Next, let's do number 3. So here's car number 3, and somehow its mass times acceleration has to point to the left. We can't do anything about its weight, so we need something which, when added to this gravity vector, gives us this. So that's interesting. In order to make the acceleration point to the left, and in the scenario we're considering be half the magnitude of the gravity arrow, we must have to have a force which points kind of northwest, right? So if you say, what do you have to add to this gravity arrow to make this mass times acceleration arrow? It seems like what you have to add points, kind of a little bit north-northwest. So it looks like this. I think that's kind of a fun vector decomposition problem. Next, let's do number 6. So the gravitational force by Earth on the carriage, we can't change, but somehow we want these things to add up to something that points up and is half the length of the gravity arrow. I think the way we arrange for that is to make the contact force point up and be 1.5 times as long as the gravity arrow. So that's kind of interesting. So in this case, for number 6, the contact force, for number 12, the contact force by the Ferris wheel structure on the carriage, let's say the contact force by the frame on the carriage points up. Here it also points up, but in this case it's only half the length of the gravity arrow for this particular value we chose. But in this case it's 1.5 times the length of the gravity arrow. So it seems like this contact force by the Ferris wheel frame on the carriage has to be quite a bit bigger for the bottom carriage than for the top carriage. That's because it wants to accelerate toward the center, and to do that it has to completely overcome gravity and then make it accelerate up in addition. Here it has to accelerate downward toward the center, so gravity is already doing most of that job, and it just has to, gravity's already doing more than enough of that job, but it has to undo a little bit of what gravity is doing. Finally, let's do number 8. So its acceleration vector points this way toward the center. Once again, we can't do anything about gravity, but we want an acceleration that goes that way. So you say, what do you add to this to get something that goes that way? I guess you have to add, well, let's see. So we start with this, and we want to end up with this. What do we have to add to get that? I guess we have to add this. It seems like in this last case, the contact force by the frame on the carriage has a big up component and just a little bit of a component to the right. So that you take the gravity vector, and then you add this contact force by the frame on the carriage, and you get this mass times acceleration vector that you want. It points toward the center of the wheel, and it has, in our unrealistic scenario, half the length of the gravity arrow. So this one, number 8, and this one, number 3, are my favorites because you have to really think about the direction that the arrow is going. But I really like this problem because you have one force that's given, it's just the weight. And then you know how big the acceleration vector should be and what direction it should be. So then you have to say, well, what's the other force? What does that other force have to be to make everything add up to get the right acceleration? I think that's fun. You attach one end of a string of length L to a small ball of mass m. You attach the string's other end to a pivot that allows free revolution. You hold the ball out to the side with the string taut along a horizontal line, as in the figure. If you release the ball from rest, what is the tension in the string as a function of the angle theta swept through? Whoa. What should the tensile strength of the string, well, it's really saying what's the biggest force. Like, what's the biggest tension the string experiences? Yeah. What should the tensile strength of the string be if it's not going to break? That really is asking, what is the biggest tension in the string throughout the motion? And I guess you might also want to know, like, at what angle does that biggest tension happen? So this is basically asking, what happens if we have a pivot here and we hold this ball out horizontally initially, and then we just let it go? So we want to say, well, what happens? So we want to know what's the tension in the string as a function of angle that the ball swings through. So we have the scenario drawn here. Here's the ball of mass m, and it's a small ball. That means we don't need to consider the rotational inertia of the ball itself. So we'll consider the ball to be tiny compared to L. So then we don't have to worry about rotational kinetic energy of the ball. We just worry about its motion as a whole, the motion of its center of mass about the pivot. So here's the pivot, and then it sweeps out this circular arc, and then we want to know what's happening as a function of this angle theta. So initially theta equals 0, and I guess if no energy is dissipated in any way, then theta should make it all the way up to pi before it turns around. And we want to ask, what's the tension in the string as a function of theta? I think we want to start by drawing a free body diagram for the ball at the moment when it is an angle theta away from its initial position. Let's see if we can analyze the forces acting on it at that moment, at that instant. Because it's moving in a circle, there must be a component of acceleration that points toward the center of the circle, but it's also speeding up or slowing down as it goes through its circular motion, so there will also be a tangential acceleration. So just the fact that it's going in a circle implies that there's an acceleration that points toward the center of the circle. But then the fact that its speed is changing as it traces out that circle means that there must be another component of acceleration. So I guess for the first 90 degrees of its motion, it's speeding up. So I think there will be an additional component of acceleration that points forward along the tangent line. And then for that next 90 degrees of its motion, it will be slowing down. So there must be a component of acceleration that points tangentially backward along its motion. So there are only two forces acting on the ball. One of them is gravity, which points down, and we know its magnitude is just the weight of the ball. And the other one is the tension in the string. And I think so that the force exerted by the string has to point along the axis of the string. It's a so-called axial force. So when theta has this value, then the direction of the string is like that. And so I claim if theta is 0, then whatever force the string exerts must point to the right. And if theta is 90 degrees, whatever force the string exerts must point straight up. And if theta is 45 degrees, then whatever force the string exerts must point at a 45-degree angle up and to the right. So I think this is the right diagram for the tension and for theta, the angle at which the tension is exerted. Now we have to figure out what to do with this diagram. At first I was tempted to decompose tension into components, but I don't think that's the right thing to do because we actually know something about the acceleration in this direction along which the tension points, because that's toward the center of the circle. So we know how big the acceleration has to be toward the center of the circle. So I think we want to decompose gravity so that we can have this component of gravity and this tension somehow combine to give us the centripetal force needed to maintain circular motion. So if we decompose gravity, we'll have one component like that and one component like that. We'll cross this off. And you see these two things would add up to the original gravity vector. We want to decompose the gravity vector so that we have one component that is centripetal and another component that is tangential. So you see one component of gravity. So here's gravity. We actually want one component that is centripetal, or actually centrifugal, the opposite of centripetal. And then we want another component which is tangential. Notice that the string is an angle theta down from the horizontal. And if we're going to say what's the direction that the string acts on the ball, then that will be an angle theta above the horizontal. So here is horizontal, and here is an angle theta above the horizontal. So there's the tension. And then gravity is down here, and we want to say, well, notice this is the radial direction, or the opposite of the radial direction, and this is 90 degrees away from that, which is the tangential direction. So if this is 90 degrees away from this, then if this angle down here is theta, then this angle down here is theta, because gravity is 90 degrees down from the horizontal. So you see here's horizontal, 90 degrees away is gravity. Here's the string tension, which is in the radial or opposite radial, it's in the centripetal direction. So then here is the tangential direction, 90 degrees away from that. So if this angle from the tension to the horizontal is theta, then this angle from the tangential to the vertical is theta. And then perpendicular to that is this radial component of gravity. Comparing this tangential part of gravity to the original gravity line, this looks like adjacent over hypotenuse. So this must be mg cosine theta. Then if we were to take this radial part of gravity and redraw a copy of it over here, we would see that this is opposite over hypotenuse. Opposite over hypotenuse is sine theta. This must be mg sine theta. One check on that is to notice that when theta is 0, cosine theta is 1 and sine theta is 0. So when theta is 0, the tangential component of gravity is very large and the radial component of gravity is 0. So that makes sense. And then when theta is 90 degrees, the radial component of gravity is large and the tangential part is 0. So I think we have this right. So let's make our two coordinates be a radial component, a radial coordinate which points out from the center of the circle, since that's increasing radius, and a tangential component which is tangent to the circle. And then we only really want to write F equals ma in the radial direction. So let's do that. The acceleration in the radial direction is minus v squared over r, since the acceleration along this coordinate points toward the center of the circle and has magnitude v squared over r. So since the radial component points out, we want a minus sign. Also, it's not really r, it's L, since we're calling the radius of the circle L. Then we can solve for the string tension. So the tension is mg sine theta plus mv squared over L, since L is the radius of the circle, because the string is of length L. Let's just recap what we did. We drew a free body diagram for the ball. Then we decomposed gravity into radial and tangential components. So here's the tangential direction, which I'm calling T. Here's the radial direction, which I'm calling R. Then we wrote F equals ma for the radial component. So mass times acceleration in the radial direction is the sum of forces in the radial direction. And we can make sense to do that because we know the acceleration in the radial direction is minus v squared over L. Then the next step is we're going to use energy conservation to write this mv squared factor in terms of the angle theta, because somehow the angle theta tells us how far down we are from the horizontal, and that will tell us how much kinetic energy we gained after losing some amount of gravitational potential energy. So let's do that next. This is some height h, and this is the same length L. Here is a right angle. So h over L is opposite over hypotenuse is sine theta. So the decrease in gravitational potential energy is mgl sine theta. In other words, the gravitational potential energy from the starting point to when we reach the angle theta decreases by mgl sine theta. Therefore, 1/2 mv squared equals mgl sine theta. We were able to write that because the kinetic energy started from 0, and the increase in the kinetic energy equals the decrease in the gravitational potential energy, because gravitational potential energy is being converted into kinetic energy. So the kinetic energy started from 0, and all of the kinetic energy came from losing gravitational potential energy. And the amount of gravitational potential energy that we lost was mg times this change in altitude. And this change of altitude is L sine theta. So the amount of gravitational potential energy that the ball Earth system lost was mg L sine theta. So that must equal the amount of kinetic energy that the ball gained. So the ball's kinetic energy must be mg L sine theta. So now mv squared must equal 2 mg L sine theta. So this line tells us that mv squared over L must equal, so this is 2 over L times this expression. So 2 over L times this expression is 2 mg sine theta. So that gives us that the tension equals mg sine theta plus 2 mg sine theta. Tension equals 3 mg sine theta. Whoa, so that was pretty tricky. So the tension that we get is 3 mg sine theta. So its largest value is 3 mg when theta is 90 degrees, or pi over 2 radian. So that's pretty interesting. I guess we can go back to the problem statement. So the tension in the string as a function of the angle theta that is swept through. So it seems to be the tension is 3 mg sine theta. And then the necessary tensile strength of the string, I guess, is 3 mg, because the maximum value of sine theta is 1. So the maximum tension is 3 mg. And that maximum tension happens when theta is 90 degrees, which is pi over 2 radians. And you can notice that on slide 59, I made this same argument that the altitude loss of the ball divided by the length of the string equals sine theta. Although I used a different variable, I said L minus y instead of just saying h. Here's a classic Physics 150 problem. This problem is considered a real challenge by Physics 150 students. A small block of mass m slides down a sphere of radius r. The block is small, by the way, so that you don't have to worry about rotational kinetic energy for the block. You just worry about movement of its center of mass, its translational kinetic energy. A small block of mass m slides down a sphere of radius r, starting from rest at the top. The sphere is immobile, and friction between the block and the sphere is negligible. In terms of m, g, r, and theta, where theta is the angle with respect to the vertical of the block current location, determine the kinetic energy of the block. So that will use a trick very similar to the trick we just used with the ball and the string. The centripetal acceleration of the block, which I guess we can get once we know the speed, and we can get the speed once we know the kinetic energy. The normal force exerted by the sphere on the block, I guess we'll get that by writing a free body diagram. and the normal force will be entirely in the radial direction, so we'll use the radial component to get the normal force. At what value of theta does the block lose contact with the sphere? So this is kind of similar to that loop-de-loop problem or the bucket spinning on a string problem with the water in it. In this case, the normal force can push on the block, but the normal force cannot pull on the block. So if we figure out what the required normal force is as a function of theta, and clearly if you look at theta equals 0 when the block is on top, then I guess if the block is on top and it's not moving or it's just barely moving, then the normal force just equals mg at the beginning when theta equals 0. But it seems like probably the required normal force will get smaller and smaller as the block slides down to bigger and bigger angle with respect to the vertical. And at some point, the required normal force to keep the ball moving in a circle will become negative. In other words, at some point, it seems like if you wanted to keep the block moving in a circle, instead of the sphere pushing on the block, the sphere instead would have to pull on the block, as if the sphere were like a string or like some kind of magnet that holds onto the block. It's at that instant when the necessary normal force switches from a positive pushing value to a negative pulling value that we say the block loses contact with the sphere. Because now it seems like in order to keep the block in contact with the sphere would have to pull on the block, and the sphere is not able to pull on the block, it's only able to push on the block. So let's see if we can work that out. So to figure out the kinetic energy, I think we have to figure out the loss in gravitational potential energy. Right, so we use the same argument that the Ke equals loss of gravitational potential energy since we started from rest. So this is the height h, so therefore this is also the height h from the center of the sphere out to this point, which is at the same altitude as the point of contact between the block and the sphere right now. So I think h over r is adjacent over hypotenuse is cosine theta. So h is r cosine theta, so the altitude loss is r minus h equals r minus r cosine theta equals r1 minus cosine theta. Since the block began at a height r above the center of the sphere, and now it's at a height r cosine theta, so it seems like the loss of altitude of the block is r minus r cosine theta. So it's r times 1 minus cosine theta. So loss in GPE is mg r 1 minus cosine theta. So the block started out a height r above the center of the sphere, and now once it's at an angle theta with respect to the vertical, it is at a height r cosine theta with respect to the center of the sphere. So the initial gravitational potential energy minus the final gravitational potential energy is mgr 1 minus cosine theta, because initially it was mgr and then later it's mgr cosine theta. So this loss in gravitational potential energy equals the block's gain in kinetic energy. So the kinetic energy, 1/2 mv squared, must equal mgr 1 minus cosine theta. Then the centripetal acceleration is v squared over r, which is just mv squared times 2 over mr. So this is 1/2 mv squared times 2 over mr. So that must be mgr 1 minus cosine theta times 2 over mr. And that must be 2g 1 minus cosine theta. Okay, next we want to draw a free body diagram for the block when it is at an angle theta with respect to vertical. So here it is initially at angle 0 with respect to vertical. So then sometime later it'll be at angle theta with respect to vertical. So in fact the problem statement already hints that there's a downward gravity force, and then there's a normal force which is pointing radially, since it should be normal to the surface of the sphere, and the surface of the sphere normal vector just points from the center of the sphere out through the surface. So here is the gravity vector, and then here is the normal force. And we want to find the radial and tangential components. We really only care about the radial component, since we want to use F equals ma for the centripetal component. So we want to decompose gravity. Let's indicate where the angle theta is here. Then let's decompose gravity. This must also be theta. This must also be theta, since this is extending the same line, this is extending the same line. So if this angle is theta, then this angle must be theta. So with respect to this original gravity line, if the gravity line is hypotenuse, then this radial part of the gravity line must be mg cosine theta, since this is adjacent over hypotenuse. And then if we had a copy of this tangential part down here, this would be opposite over hypotenuse. So then this is adjacent over hypotenuse, which is the gravity centripetal component over mg. Okay, so we decomposed gravity into a centripetal component that points toward the center of the sphere, and a tangential component, which is tangential to the surface. And we really don't care about this tangential component, although it is what causes the block to speed up as it goes. What we care about is this centripetal component, since it will help us to figure out how big the normal force needs to be to continue to execute circular motion. Now we can write Newton's second law for the radial coordinate to figure out how big the normal force is. So the centripetal direction is this way. So that gives us the normal force is mg cosine theta minus mv squared over r. Now we can use this result up here to write this mv squared over r term in terms of theta. So it seems like when cosine theta is, it seems like when theta is 0 at the very beginning, cosine theta is 1, and so then we have that the normal force equals mg. That makes sense. The block is not moving or just barely moving, and it's right on top. So the normal force equals mg. And the normal force gets smaller and smaller. Eventually, the required normal force to keep the block moving in a circle around the surface of the sphere becomes 0, and then it becomes negative. So the block loses contact with the sphere when this normal force becomes 0. In other words, when it goes from being positive outward to being negative, which would be inward, which is impossible for a force that can only push, it can't pull. So when this expression equals 0, the block loses contact with the sphere. So that means when 3 cosine theta minus 2 equals 0 is when the block loses contact with the sphere. So the block loses contact with the sphere when the normal force goes from positive, which would mean pushing, to negative, which would mean pulling, which is impossible for the normal force to do. In other words, that boundary from positive to negative happens when F normal equals 0. Let's figure out when F normal equals 0. So the block loses contact with the sphere when cosine theta equals 2/3. In other words, when theta is arc cosine of 2/3, which is about 48 degrees down from the vertical. So actually the block loses contact with the sphere sooner than you might guess. And I guess that's because it's gaining speed as it goes down. So somewhere around here it seems to lose contact with the sphere. This is a problem that most Physics 150 students have a really hard time figuring out. So if you can understand it, you will have really achieved something.